Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the fifth summary in the Padisco Statistics video series. This summary is about probability distributions. In particular, we'll be going over discrete random variables, the binomial distribution, continuous random variables, and the normal distribution. Now, the first few summaries were all about data that have already been collected. And of course, we can talk about how such data are distributed by showing some charts or by measuring an average and so on. But this data will always come from a variable. And to start exploring statistical inference, which is where we try to use statistics to actually say something about the world, we're going to have to focus on more than just data. We're going to have to study the underlying variable too. In a way, the important difference here is that instead of studying data, so that we can say what a variable did do, we're going to study probability, to study what a variable can do. That's where probability distributions come in. So to begin our look at probability distributions, we start by defining a random variable. They're probably best explained with an example. Suppose you have a coin, and you want to flip the coin twice and count the number of heads that show up when you do that. There'll be either 0, 1, or 2 heads. Now, you could treat this as a data situation. You could do this double coin flip 100 times, for example, and then you would have 100 data values. You could even then start describing that data by showing a relative frequency table or a histogram. But how about we don't collect data and instead just think about what variable we're looking at here and what values it could take. As I just said, there are 3 possible values it could take: 0, 1, and 2. And the probabilities of these 3 values are shown in this table. When we think about what a variable could do instead of what it did, that's when we call it a random variable. To be more precise, a random variable x is a variable that can assume a numerical value for every outcome in a sample space. And a random variable is discrete if the sample space can be put into a list of separated items. For example, our coin flip experiment gives a discrete random variable because the sample space is just 0, 1, and 2. Later in this summary, we'll go over the other kind of random variable, continuous random variables. Now, when we just assigned the 3 probabilities to those 3 outcomes for the coin experiment, what we were doing was assigning a probability distribution. A probability distribution is a function that assigns a probability to each and every outcome for a discrete random variable. So again, here is the probability distribution for the variable underlying the coin flip experiment. Notice that it looks a lot like the relative frequency table that came about when we collected 100 data values. The difference is that the relative frequency table will vary from sample to sample. The probability distribution tells us about the fixed nature of the underlying variable. We can also draw what is called a probability histogram, which is analogous to a data histogram, except that instead of reflecting what the variable did, it reflects the probabilities of what the variable can do. We can also, like we do with data, measure the random variable. If we have a discrete random variable x with a bunch of outcomes and a probability distribution giving probabilities to all those outcomes, then the expected value of x is given by this formula. The expected value is like the mean, and in fact we often call it the mean of x. The variance of x is given by this formula, and the standard deviation is the square root of the variance. Not surprisingly, the variance and standard deviation are analogous to their counterparts in data measurement. That's discrete random variables. Now let's have a look at the most common discrete probability distribution, the binomial distribution. Suppose you're a quality control inspector at a light bulb factory. You're about to test 20 light bulbs to check that they work, and you'll discard any that don't. Let's say you know that overall 3% of the light bulbs that your factory makes are defective. What's the probability, for example, that exactly 2 are defective in the 20 that you're about to check? If we let x be the random variable that tells us how many are defective, then the sample space for x is the set of all numbers from 0 up to 20, because there can be anything from 0 to 20 defectives. And the binomial distribution for x is given by this formula. The x in that formula is the number of defectives, and the formula itself, P of x, is the probability that the number of defective light bulbs is x. You can plug in any whole number for x from 0 up to 20. This formula will tell you that the probability that there are that many defectives. For example, if we let x equal 2, the value we will get is 0.0988. So the probability that exactly 2 of the 20 light bulbs are defective is around 9.88%. Now there are actually lots of different binomial distributions because the formula would change if you were to check a different number of light bulbs, or if you change the probability that each individual light bulb is defective. So let's say in general that you check n light bulbs and that the probability that each one is defective is p. The probability that x light bulbs are defective is then given by this formula, and that's the binomial distribution in general. The binomial distribution is very important for discrete random variables, but actually a lot of interesting random variables are continuous. So let's look at that now. A random variable is continuous if its values exist along a continuous spectrum. For example, if your variable is measuring the length of time it takes for a ball to drop to the floor, that time taken could, for example, be anywhere between 1 second and 2 seconds. The way we assign probabilities for continuous random variables is different to how we do it for discrete random variables. We do it through a probability density function. A probability density function is a function f of x that assigns values to a continuous random variable x, such that firstly, the values are always positive, so the curve f of x is always above the x-axis. And secondly, the total area underneath the curve f of x is always 1. Here's an example of what a probability density function might look like for a continuous random variable. Once we've assigned a probability density function, then we can talk about probabilities with continuous random variables by using the following rule. Given two different values, a and b, for x, the probability that x will assume some value between a and b is equal to the area under the curve f of x between a and b. So that's continuous random variables, and the most common distribution for continuous random variables is the normal distribution. Like the binomial distribution, there are actually infinitely many normal distributions, but once you specify the mean and standard deviation, you've specified a particular one. The probability density function for the normal distribution with mean mu and standard deviation sigma is presented here. It's quite nasty, but don't worry, you won't need to actually use it. But just so you know, the general look of this probability density function is a smooth bell-shaped curve as shown here. All normal distributions will look more or less like this. We get around having to use the complicated formula by using the standard normal distribution, z. Z is the normal distribution with a mean of 0 and a standard deviation of 1. Its probability density function is presented here. Still fairly nasty, but the good news is that someone has done all the hard work for us. There's a thing called a standard normal table, which has lots of values that were calculated by using the probability density function for z. Here's the standard normal table from the Padisco textbook. And if we're given a particular value in z, the table tells us the probability that z will assume a value less than it. That is, the area of the curve to the left of that value. Using some simple arithmetic, you can then always answer questions like, what's the probability that z will assume a value greater than it? Or what is the probability that z will fall between two given values? And the other helpful thing about z is that any normal distribution x can be transformed into z using the transformation formula. The best way to familiarise yourself with this is to get practice, so let's go to the Padisco workbook to give a question a go. In this question, an education department is considering providing an assistance program for students with an IQ in the bottom 5% of the population. You're told that these IQs follow a normal distribution with mean 98 and standard deviation of 21. You're being asked to calculate the cutoff IQ that would make a student eligible for the assistance program. This question can be answered by using the transformation formula and the standard normal table, which I did earlier. So if you put the answer in, you can see we get personalised feedback and an explanation of the question. So that was probability distributions. The key topics were discrete random variables, the binomial distribution, continuous random variables, and the normal distribution.